Okay, hello everyone. We would continue with function spaces. We are going to continue what we ended yesterday, where we finished yesterday. And yes, we do have a meeting on Friday. So you are going to have a link for Friday. So if you look at the Zoom, there would be a link for tomorrow, scheduled for Friday. So let's continue what we were discussing. We were talking about space of functions. Let's remember what we were doing. We were talking about, well, we started with Fourier series of a function. So we learned sometimes for a periodic function, say a real valued function with period 2 pi, we can write that as an infinite series. We can write it, at least sometimes, apparently, we can write it at a naught plus sigma an cosine nx plus bn sine nx, where n goes from 1 to infinity. And then we started computing these coefficients, a naught, an, and bn. What are these coefficients? We computed these coefficients, but if you remember how we did that, at some point, we took, for example, for computing a naught, we took integral of everything in this equation from minus pi to pi, minus pi to pi, minus pi to pi, dx, dx, dx. All the integrals are with respect to x. And at some point, if you remember, we interchanged the place of integral and series. We said, let's assume the integral of the sum of these functions is equal to the sum of integrals. And then we computed these integrals and we got to something. We talked about that. I'm not going to repeat that. But the point was that then we raised this question that, is it correct? Is it correct that we can change the place of integral and the infinite sum? These series go to infinity. And in the class, we constructed a counterexample. So we noticed it is not always correct. So we found a counterexample for this. In another sense, we found a sequence of functions fn of x, such that if you look at their sum and take integral, say from a to b, the result is not equal to the sum of the integral of these functions from a to b. So we notice this is not always correct. So when we notice this is not correct in general, we started to think why we assume that in the case of Fourier series. So although it is not correct general, sometimes this equality is correct. So sometimes we have equality. There are some extra assumptions needed for that. So if we want to have equality here, some extra assumptions are needed. So we started to talk about these sorts of problem, and one very important, so we started to think about these questions. Well, we can now set the Fourier series aside and really just think about this problem first. This is a basic problem in analysis, mathematical analysis, and it's related to sequences of functions. So this problem is actually related to more basic questions related to sequences of functions and function spaces. So if I just review what we did the other day, we talked about a sequence of functions which converges to another function, but we noticed there are different ways a sequence of functions can converge to another function. And we learned about two very important different ways that we would say this sequence of functions is converging to another function. One of them was pointwise convergence. And the other one was the uniform convergence. Okay, so remember, for example, we said the sequence of functions fn of x equals x to the n, defined on an interval 0 to 1 to r. This sequence of functions, as n goes to infinity, converges to f of x equals to 0 when x is not equal to 1, and it's 1 when x is equal to 1. However, this sequence of functions does not converge to the function f uniformly. We finished the previous meeting with an important theorem that if we have a sequence of functions defined on some interval, let's say to r, where these functions, all of them are, say, they all are continuous at some point x naught, that would imply if this sequence of functions are converging uniformly to another function, then that other function is also continuous at x naught. This is what we proved the other way. And the proof was by this epsilon over 3 method, which we used a version of triangle inequality. That's what we did in the previous meeting. So I'm going to continue from here.
Proof by what?
Epsilon over 3 method. So what we did was we broke the problem into 3 pieces. So if you want just to review that, so in order to show if is continuous at x naught, we said we should show what was the definition of continuity. The definition is this: if we should show for any positive epsilon, for any epsilon greater than 0, there exists delta greater than 0, such that if we have an x, which its distance from x naught is less than delta, then the distance between f of x and f of x naught is less than epsilon. And what we did, we broke this problem into 3 pieces. So in some sense, we used the fact that fx minus fx naught can be written as fx minus fnx plus fnx, they would just cancel each other, minus fnx naught plus fnx naught, they would also cancel each other, minus fx naught. Right? These two cancel each other and these two would cancel each other, so they're equal. And then we noticed this, we kind of grouped this quantity into 3 different parts. And then we showed each part can be, we can make each part quite small. We can make this part less than epsilon over 3, this part less than epsilon over 3, and this part less than epsilon over 3. And in some sense, their sum would be less than epsilon. The reason we can make this one less than epsilon over 3 was because fn is converging to f uniformly by assumption. This one is less than epsilon over 3 because fn is continuous, and this one can be made smaller than epsilon over 3 because fn goes to f uniformly. So that's what I mean by the epsilon over 3 method. So this is what we did yesterday. Is there any question about things we talked about? If there is any question, I can answer that, and then after that, we can start our new topic. Okay, now I want to kind of think about the same problem with slightly different perspective. Suppose I define a set. I would show that set with C, B. Let's just use a diagram for that. Suppose every element in this space, every point is in this space itself is a function. Okay. Suppose I have a set of functions. So let's say the set of functions, let's say the set of functions CB, say A, B, R. By that, I simply mean, suppose this is a set of functions F from A, B to R, where this function F is bounded. Okay, suppose this is the set of these functions. So any point here is a function itself. Okay, for example, x to the n, f of x equals x to the n is a function there. Okay, right? Or f of x equals sine of x, that is another point there. Any bounded function from an interval, for example, 0 to 1, or any interval, that really doesn't matter here. From any interval to R, it's just one element in that set. Okay, so the points in this set themselves are functions. Okay, and so now we have this kind of space of functions. This is very schematic, that when I show it with just like a circle and I would tell you each point is a function, it's just a way of thinking about it. Okay. Now we have this set. In some sense, I want to define geometry on this set. I want to tell you we can define distance between different functions. So if this point here is xn and this other point here is sine of x, two different points in this space of functions, I want to tell you it's possible to say how far these two functions are from each other. In another sense, you might think xn and sine of x, probably their distance is greater than, for example, the distance between the function x, for let's say x to the n plus 1 over 1000. So probably these two functions are quite close to each other. They look very similar, right? If you look at x to the n and x to the n plus 1 over 1000, they seem similar to each other, but x to the n and sine of x, maybe, well, it depends on actually our interval, but probably they are not as similar. So I want to say that they are far from each other in some sense. So we like to define distance between functions. We want to say how far two different functions are from each other. Great, that's the goal. So our goal here is to define what is called actually either the distance between functions or also called metric. Okay, how would I do that? So that's the question, that's the problem. Now have that in mind, and for a moment, let's think about another perspective. Suppose I have a function f defined on some interval a and b to r, where f is a bounded function. Okay, so by bounded I mean, if you look at, let's say if we are looking at the graph of the function, it simply means f would have an upper bound and have lower bound. For example, I would say this is the upper bound and this is the lower bound. And the graph of f would be between these two things. For example, the graph of f would be something like this. It doesn't even need to be continuous. It might be discontinuous function, but as long as it has an upper bound and a lower bound, it would be bounded. But, well, you're familiar with many unbounded functions. For example, consider this function, which goes to minus infinity. There is no lower bound. It just keeps on going down on the given interval. Okay, it can even be like maybe at 0, it's even equal to 0. I can define the function in a discontinuous way, and I can even extend it. I can have a function like this, for example. Suppose this is the graph of the function. So at some point, it goes to minus infinity. So it is not bounded. So this is an example of a bounded function. And this is an example of a function which is, it's not bounded. Okay, suppose now f is a bounded function. I would define something called norm of f. And usually we just write sup here. It simply means look at the value of f of x for every x in this interval, in the domain of the function. Here I'm assuming the domain of the function is a given interval. And look at absolute value of that. Okay, this would be a set. And this is a bounded set. And take supremum of this thing. Take supremum of this set. Okay, so for example, if, well, let's just look at an example. For example, if f of x is equal to sine of x, and if we are taking the interval, I don't know, from minus pi to pi, let's say we are looking at this on the interval minus pi to r, the norm we defined for f would be supremum of the values of f with absolute value, which is, of course, 1. Sine is always between -1 and 1, and in this interval, it has both values, and its absolute value would be 1, right? So I define that to be the, usually it's called sup norm of f. Okay, there is an alternative name. Sometimes it's called L infinity norm of f. There is a reason for that name, which here we are not going to talk about that. Okay, so this norm satisfies some properties. There are some properties it satisfies. First is this fact. Norm of a function, any function, is of course greater or equal than 0, right? Because it's supremum of a set which everything there is positive. 2, if norm of a function is 0, it implies the function itself is 0. Because if the is constant 0, right? It's always 0. Because if this function is not the constant function 0, at some point it would be non-zero, and then the absolute value of that non-zero number would be greater than 0, so the supremum would not be equal to 0. The other property is that if we multiply the function by a constant number c, the supremum would be equal to absolute value of c, so it can be negative, times norm of f. And finally, we have the triangle inequality. If we have two functions, if we look at its supremum norm, the sup norm would be less or equal than the sup norm of f plus sup norm of g. Okay, these are the kind of basic properties of this norm we defined. Now, going back, if I have two functions, let's say one of them is f of x, the other one is g of x, two functions. If I want to define a distance function between them, if I want to say how far these two functions are from each other, that the definition the definition I would give is this one. So the distance between f and g, I would just write d of f and g, would be the subnorm of f minus g. And that kind of makes sense, right? For example, if you have two numbers like 5 and 3, if you want to say how far they're from each other, you would subtract them and look at the absolute value of that, right? So here for functions rather than absolute value, we have this subnorm. So this is simply equal to supremum of absolute value of f of x minus g of x for all x in the interval they are defined. Let's say they are defined on the same interval. They share the domain. Okay. Now, kind of a third definition for convergence comes to mind now. I can say a sequence of functions fn is converging to f if the distance between fn and f is going to 0 as n is going to infinity, right? That makes sense, right? I would say sequence of functions, fn, say f1, f2, f3, etc. This sequence I can say is converging to f if the distance of the elements of this sequence and f, the distance, is converging to 0. That gives another definition of convergence. So we have the pointwise convergence, we have the uniform convergence, and we have subconvergence. Now that we have these three properties, we can think about the relations between them. We have already seen that pointwise does not imply uniform convergence. It means we have a sequence of functions which they converge to another function in a pointwise manner, but they do not converge to that function uniformly. What about the other relations? How the other things are related to each other? That's now the question. The interesting thing is that uniform convergence and convergence with respect to sup, they are actually equal. So uniform convergence and subconvergence are equal. So subconvergence implies uniform convergence and uniform convergence implies subconvergence. And another interesting fact is that although pointwise convergence does not imply uniform convergence, the converse is true. The uniform convergence implies the pointwise convergence. Okay. And of course, therefore, supremum convergence implies pointwise convergence, but pointwise does not imply supremum convergence. Okay. Now, is there any question here? Okay. Great. Now let's look at a theorem. One definition and one theorem. So let's go back to for example, real numbers, the set of real numbers, and think about the very specific subset, the set of rational numbers inside real numbers. These two spaces, they have a difference, a fundamental difference. We say the set of real numbers is complete, but the set of rational numbers is not complete. What do I mean by that? It means the set of real numbers, this set does not have any holes, but there are gaps in Q. There are gaps in Q, right? For example, when you are looking at the set of real numbers, we can think about the set of real numbers as a line. For example, here we have 0. Here we have square root of 2. This number is not rational, right? So if I'm looking at the set of rational numbers, it does not have this specific point. There are a lot of irrational numbers. So if we are looking at the set of irrational numbers, there are a lot of gaps and holes between them, and they correspond to irrational numbers, right? That kind of space is called space which does not have any gap, is called complete. So the rigorous way to define that is this. If you have a sequence, say AN, suppose it's a sequence in rational numbers, this sequence might be Cauchy. It might be Cauchy, but not convergent. What do I mean by that? So what is the square root of 2? Let's look at this number up to a few decimals. So suppose we have this sequence of rational numbers. Suppose A1 is equal to 1, A2 is equal to 1.4, A3 is equal to 1.41, A4 is equal to 1.414, etc. This sequence is converging to square root of 2 as a subset of real numbers. So if we are in R, if we are living in the set of real numbers, we would see this sequence, which I just wrote in the previous page, is converging to a square root of 2. On the other hand, we have the same points in Q. All of the points, all of these numbers we have here, they're rational. These numbers are rational. So if all of our world consists of rational numbers, I can still look at this sequence. I have these points. But my world does not have square root of 2. So I would say it does not converge to anything. I would say it's not convergent, right? Because the limit does not exist in my space if I'm living in Q. I would see I have a sequence of points. They are getting closer and closer to each other, but they are not converging to anything. So in Q, I have a sequence of points where they are getting closer to, it seems they're getting closer to something, but not really, because the limit is not there. So the important property here is this sequence is Cauchy in the sense that the points of the sequence, say AN and AM, if I take two elements of this sequence, as N and M are increasing, they are getting closer and closer to each other. So the distance between these points is getting very small. So if I'm in Q, and if this is square root of 2, which does not exist actually in Q, it is not there. If I look at this sequence AN, I would say this is A1, A2, A3, A4, A5, 6, 7, 8, 9, 10. They are getting very close to each other. So these subtractions, they become very small. But the sequence of AN is not converging to anything. So it is any sequence which these terms, the distance between the elements of the sequence as we are increasing N and M is becoming very, very small. It's called Cauchy. But this Cauchy sequence is not convergent, not convergent. So if you have some space X, any space X, which there for any sequence there, for any sequence AN there, if being Cauchy, implies being convergent, it means in that space there is no hole, there is no gap. And we call that space X complete. But if for another space Y, if there is a sequence there which is Cauchy not convergent, it means that space has gaps and has holes, and this space is this space is not complete. Okay. Is there any question about the definition, or is the definition clear? Okay. So that's the definition, and it makes sense for any space. Here, the space X doesn't necessarily need to be R or Q. It can be the space of functions. So that's our theorem. So for any interval, fixed sum interval A and B, the set of bounded functions defined on this interval, so the set of bounded function defined on this set of functions F from A to B to R, which this function is bounded, with the supremum, with the sup metric I defined. So here I'm talking about the distance between functions. Now, if I have sup metric for any two functions F and G here, I can define their distance to be the sup of F minus G. That's the distance between F and G. This space with this metric is complete. So this set of functions does not have any hole, does not have any gap. So think about this huge space of functions, which every point there is a function, a bounded function. This space does not have any hole, does not have any gap, it is complete. This is not something which maybe it's not a good place to talk about it, but I like to tell it to you. When we think about R, we think about some one-dimensional thing. Schematically for this set, I just drew a diagram. I said, suppose F is here, G is here, we are defining the distance. But in this drawing, it's something two-dimensional. But can you guess this space? This is not really about our course, just a random kind of question. But can you guess what is the dimension of this space? What is the dimension of space of functions? I have not defined what dimension is. It's just an intuitive question. Does anyone have any guess? What is the dimension of this space? Yeah, that is correct. It's an infinite dimensional space. That is true. So this is an infinite dimensional space. And that's partially why studying, well, I think that's the most important. That's really one of the reasons why these spaces can be very complicated. Anyway, that's not related to our course. So I would erase that. Now the point is that I want to prove this theorem. And we have everything in order to prove this theorem. We have every tools we need. We know what is the definition of this space, and we know what does it mean for space to be complete. So I want you to try to prove that. So let's think about this maybe for 5 minutes. It's an interesting problem. Try to prove it, and then I would prove it. Okay? Okay, let's try to solve it together. So we have a space, this CBABR, and we want to show this space is complete. So by definition, it means what we want to prove is this. We want to show for any Cauchy sequence, suppose we have a Cauchy sequence of functions Fn, We want to show, so this is our assumption. We have a Cauchy sequence. We want to show this is convergent. Fn converges to another function f in this space. I would drop ABR from now. I would just write CB. So first of all, what does this convergence mean? Convergence with respect to what? With respect to, is it pointwise convergence or uniform convergence? What do I mean? What do we mean by the convergence here? What type of convergence we are referring to? That's the first question. Yeah, so uniform convergence is correct. So when you see here, I wrote plus submetric. It means this is the way we think about convergence. So it means convergence with respect to submetric. But submetric is the same as uniform convergence. Yeah, so it's either, well, they're the same actually. So uniform convergence, which is equal to convergence with respect to submetric. That is correct. So what do we want to show? We want to show that if Fn is a Cauchy sequence, so for every n, we have Fn defined on A and B to R, where the only thing we know about them is that they are bounded. We want to show this sequence is convergent. What does that mean? So what does it mean for Fn? What does it mean for Fn to be convergent? It means there is a function f in our space CB, which that means f is a function from AB to R and bounded. Where Fn converges to f with the supremum norm. So Fn converges to f with supremum norm or submetric. That's what we want to prove. Now, converging with supremum is the same as saying the distance between Fn and f is going to 0. Right? Supremum norm means with respect to this metric. So it means the distance between these functions Fn and f is going to 0. But what is the definition of this distance? Let's just write down what is the definition of this distance. So d of Fn and f, it is defined to be supremum of absolute value of Fn of x minus f of x for every x in the interval. Right? So for each x, we can look at Fn of x and f of x. There are two real numbers. We can subtract them. Looking at their absolute value, we would get a set. This set is bounded set because both Fn and f are bounded. So if we subtract them, the result would be bounded for any n. It would be bounded. So we want to say this thing is going to 0 as n is going to infinity. But the main difficulty is that, let's go back to our assumption. Our assumption is that, what is our assumption? The assumption is that Fn is Cauchy. In the assumption, there is no word of f. What is this f? This f has no part in the assumption. Where can I find this f? That's one difficulty to overcome. How can I find f? What is this function f? So how can I find f? Okay, that's the question to answer. So how can I find this function f? So if I want to find f, I know f should be a function from a to b to r, right? So in order to completely find out what this function f is, I should know what is f of x for any x in this interval a to b, right? I want to know what is this f of x. So let's guess. First, let's guess what's the value of f of x. Well, you know, we have this sequence fn. So I know what is fn of x. I know what that is. And if I look at fn of x for any n, it would be a sequence of real numbers, right? It would be just a sequence of real numbers. So it makes sense to see what is the limit of this sequence. If they converge to anything, and if this sequence converges to anything, or if it's infinite or a finite number or not. So in another sense, I would define the function f like this. For any x, I can look at fn of that x, and it would give me a sequence of real numbers. And I can look at the limit of this sequence. And if it's convergent, it would be a real number. I would define f of x to be that real number. If the limit exists, if it exists for every x, if I can compute this limit for every x, I would have f of x for every x, and therefore I would have f. So if this limit exists for every f, then it completely gives me the function f. So the main question is that, does this limit exist or not? I'd like you to think about that. Yeah?
Do we also need to show that f of x is continuous? We're dealing with continuous functions, correct?
No, the assumption here is bounded, right?
Oh, so CB is just any bounded function.
Yeah. So B
okay.
here actually refers to functions being bounded. That is correct.
Oh, I thought the C meant continuous, but okay, thank you.
Yeah. Okay, now think why this limit? What is the reason that? Do we have a limit here? Is it defined or not, or is it finite or infinite? Okay, so we have for any x in this interval a to b, we can look at fn of x, and we can take limit as n goes to infinity. So one thing to note is that because fn as a sequence is Cauchy, it means that the functions in this sequence are getting closer and closer to each other. So functions like fn and fm, as we are increasing n and m as variables, these functions are getting closer and closer to each other. What do I mean by close? I mean with respect to the metric we have, with respect to the supremum metric. This thing is becoming smaller and smaller. In another sense, for any epsilon, for any positive epsilon, I would just take epsilon over 2. That simplifies our work a little bit, doesn't matter. For any positive epsilon, if n and m are large enough, in another sense, there is a very big number n, such that if n and m are larger than that, fn and fm would be closer to each other than epsilon over 2. In other words, their distance would be less than epsilon over 2. Okay? It means supremum of fn of x minus fm of x. If you look at these numbers for every x, this would be less than epsilon over 2. Now, if supremum is less than something, each of them are less than that. So it means for any x, if you look at each of them, not their supremum, but each, for any x, each subtraction there, if I look at its absolute value, that would be also less than epsilon over 2. It means that fn of x, after fixing a point x, fn of x is a sequence of real numbers. It's not a sequence of functions anymore. That's the important thing to have in mind. When you fix one element x and you look at fn of x, you would get a sequence of real numbers. That sequence, it means that sequence, its elements are getting closer and closer to each other. So it's a Cauchy sequence, but a Cauchy sequence in R, not a Cauchy sequence in the space of functions. Right? But what is the important thing about the Cauchy sequences in R? The important thing here is that R is complete. In other words, any Cauchy sequence is convergent. So if this sequence is Cauchy, there we know it is convergent. So fn of x converges to something. It does converge to some number, to some real number. Say f of x. This is some finite real number. This is not infinite. And being Cauchy is enough. Actually, we did not use boundedness here. Anyway, so the limit does exist for every x. So for every x in this interval, I can look at fn of x for a different n. I can take limit. I can send n to infinity. The limit exists. It's a real number. I define f of x to be that. Now that f of x is defined for everything, I would get a function f, and it's defined all over R. And it's a bounded function because for every x, we have a real number. Does that imply it's a bounded function? So let me write that as a question. I want to say the limit is inside our space, right? The limit of this sequence, if it wants to be convergent, should be inside our space. So is f inside our space? In other words, well, our space is the space of bounded functions. Is f bounded? So that's the question. You know, in general, limit of a sequence of bounded functions might be unbounded. For example, the constant function fn of x equals to n, constant n, it's a bounded function, right? It's constant. But their limit is going to infinity, n, n plus 1, n plus 2, etc. But the point here is that fn of x equals to n is not Cauchy. Here we have extra assumption. Fn is also Cauchy. Does that imply our function f here is bounded or not? The answer is yes, f is bounded. How can I see that? So we know that the sequence fn is converging to f, right? Well, that's another interesting thing that we should actually address here. So maybe it's better to first answer this question. We defined f of x as the limit of fn of x. as n goes to infinity. That was the way we defined f. Does it imply that fn is converging to f? I mean, it might look trivial, but it is not trivial. Does anyone first tell me why this statement, why this question is not a trivial question? I defined f as the limit of fn. Why am I asking, is f converging to fn converging to f? There is a non-trivial thing here. Does anyone know what is the non-trivial part? No, that's not the non-trivial part. The non-trivial part here is this. When I'm here telling you f of x is limit of fn, it means in some sense fn is converging to f. That's how it's defined. But what type of convergence is this? I'm telling you f of x is limit of fn of x for every x. What type of convergence is this? It's pointwise. That is correct. Here I'm asking you, is fn converging to f in this space CB? So when I'm asking if a sequence of functions is converging to another function or not inside this space always comes with its own metric, with its own distance function, and that's the sup, which is the same as uniform. So here the question is about the uniform convergence. And I told you in general, pointwise does not imply uniform. In general, pointwise convergence does not imply the uniform convergence. However, here it might be different. Here we have extra assumptions. And our extra assumptions actually prove we have the uniform convergence too. Here, the sequence fn converges to f uniformly too. And that's because fn is Cauchy, but it's Cauchy in the uniform way. Okay, so the answer is yes. Fn does converge to f with respect to sup norm or uniformly. How can I prove that? Well, I should show that I would say fn is converging to f with respect to sup if d of fn and f, the distance between fn and f, is going to 0. What is the distance? The distance is supremum of fn of x minus f of x for every x. I should say this goes to 0 as n goes to infinity. Why do I have that? Why do I know that supremum is going to 0? So the point is that I want to show supremum of, let's write down that again. Sup of fn of x minus f of x. I want for all x in the interval, I want to say this thing is going to 0, which means I want to say this can be made, I can make it as small as I want. It means for a sequence going to 0, it means this thing can become as small as I want. So I can make it smaller than, say, epsilon. So if for any positive epsilon, if I increase n, I would get this thing. If this thing becomes smaller than epsilon, then fn is converging to f. Okay. If I want this to be true, it means if supremum of a set, if here I have a set, if I want the sup to be smaller than epsilon, it means everything inside that set is smaller than epsilon. So it means Fn of x minus f of x, the absolute value is less than epsilon for all x. If it's correct for all x, if all of them are smaller than epsilon, their sup would be also smaller than epsilon, and vice versa. Okay? The point here is, it is true, I can do that. I can make this thing as small as I want because I know Fn of x is converging to f of x. So there exists some, say, n, such that for n greater or equal than n, Fn of x minus f of x is less than epsilon. However, this is a very good place to practice doing regress proofs. There is a gap in my argument. I can say because Fn of x is converging to f of x, so their distance is becoming, I defined f of x as the limit of Fn of x. So their distance is becoming smaller and smaller. So this thing can become smaller than epsilon. So here you go. If it's correct for every x, Fn of x minus f of x is smaller than epsilon, then their sup would be smaller than epsilon. But the point here is that the difficulty here is that I said there is some, well, there exists some n such that for any n greater or equal than that, we have this thing. The difficulty here is that this n depends on x. For different values of x, this n might be different. And that is the source of difficulty. Okay.
Oh, Professor?
Yeah.
So based on the other question you asked us when it was like, is f bounded? So if you show that the I don't know how to say it, the sup of the two functions and it goes to 0, that's how you can tell if it's bounded.
Would you repeat the sup of two functions is going to 0? What do you mean by that?
N and f.
Uh-huh.
If that goes to 0, that's how you can tell if it's bounded.
Well, the point is that, you see, that's almost what we should do. But the point here is that we have two variables here. One is n and one is x. And both of them are variable. So each Fn is bounded, right? But the sequence Fn, as you change n, they might go to infinity. That does not happen here, and that's what we are going to prove. That's what we are going to use. But you know, potentially, the fact that each of them is bounded does not prove f is bounded. But you are you are right. What you are thinking is correct. So that's kind of is the answer. So take some n, just for example, the n I have here. The point here is that if I show Fn of x minus f of x is less than epsilon for every x, that proves f is bounded. If I fix n and if I have it for every x, that proves f is bounded because Fn is bounded and f is very close to Fn, very close to Fn. And when we have a bounded function and another function is very close to that, that other function is also bounded. You might say this is exactly what we have here. Not completely. The point here is I don't have that for every x here. I fixed one x. In this line, I fixed one specific x. But it's easy to get from this line to this one. So what I need to show is that there there is some, say, n, such that for n greater or equal than that, for every x in this interval, fn of x minus f of x would be less than, say, epsilon, because we know fn is bounded, and because f is close to that, if we prove this thing here, that would show f is bounded. And this is correct. Why? Fn of x, this is very similar to what we did yesterday. This is equal to Fn of x, say, minus some Fn of x plus Fnx. Nx is the number I mentioned in the previous page. By triangle inequality, this is less than Fn of x minus Fnx. Sorry, there's also x here. Right? Now, this thing here would be, I can make that as small as I want. I can assume this is smaller than epsilon over 2. Why? Because for any nx, fn and the other n, they are two elements of our Cauchy sequence. And our Cauchy sequence, well, of course, the elements, they are getting closer and closer to each other. So their distance at some point would be less than epsilon over 2 if these two ends are large enough. Plus, I can also assume this thing is less than epsilon over 2, because for the specific x and this nx there, fn of x and f of x, I can assume are close to each other, and their sum would be epsilon. So that is the proof that f is bounded. If you did not have some analysis course before, you might find this proof a little confusing. I know that, but it's good if you start to getting involved in proving these theorems. This proves two things. It proves both f is bounded and fn is converging to f uniformly, or with respect to subnorm. I mean, it proves both of them. And because this thing is bounded itself, it shows fn is convergent to something. And therefore, any Cauchy sequence is convergent, which means this space CB is complete. So any sequence of functions defined on this subset AB, which they are bounded, if they are Cauchy, they would be convergent. They would converge to another bounded function. So if you did not follow the proof completely, I would also write down the proof in the notes more carefully. You can read that again, and you can kind of start to get used to these proofs, analytical proofs. Okay. Now, one interesting fact is that if I show the set of continuous functions on this interval AB to R, if I show the set of continuous functions on AB to R with a C0 ABR, and if I show the set of bounded functions from AB to R with CB AR, these two sets, they are kind of related. Does anyone know how these two sets are related to each other? What is the relation between these two? There is a set theoretic relation between these two things.
The continuous functions are contained in the bounded ones because it's a closed interval.
That is correct. So any continuous function on a bounded subset, this finite subset A to B, is also bounded. Of course, the other direction is not correct. We can have a bounded function which is not continuous, right? This is a bounded function which is not continuous. But the other direction is correct. If we have a function on this interval a to b, if it's continuous, it has to be bounded. It can't go to infinity. Why is that? This looks fine. This looks continuous. What's wrong with that? The problem here is that this interval is closed. So b is part of the domain. So we should have something for f of b. So if it goes to infinity, what is f of b? It should be something. And then this function is not continuous anymore. It goes to infinity and then f of b is something else. So you might get the feeling here that the continuous functions on closed intervals, finite closed intervals are bounded. This is actually, this is in a lot more general sense. If you're familiar with topology, this is an instance of a theorem which says you don't need to know this, but if you're familiar with this, probably you can understand this. The image of a compact subset under a continuous map is compact. But it doesn't matter here for us. The only thing which matters is that when you have a finite closed interval and you have a continuous map, a continuous function, this function would be also bounded. Okay, let's continue. Anyway, so what we learned up to this point is that we have two different types of convergence. One is pointwise convergence. The other one is uniform convergence, which is the same as convergence with respect to soup. Let's continue. Okay. Oh, the other thing we just learned is that the set of continuous functions defined on some interval a to b, closed bounded interval, is a subset of bounded functions defined on this interval. Okay. Now, we proved another theorem the other day. We showed that if we have a sequence of continuous functions, and if they converge to another function f uniformly, that function would be also continuous, right? In another sense, it means this set C naught inside CB is closed. So very schematic, if I want to have a picture in mind, this is CB, and then there is C not inside it. It means if I take a sequence of functions inside this C naught, like F naught, their limit would be inside this space itself. So they would convert, if they converge to something, that function is also inside C naught. These spaces are called closed spaces, right? So a very simple example of this, which you are familiar with, consider this open interval, 0 and 1 subset of R. This subset, we say it's not closed in the sense that if you look at the whole R, and then if you look at the interval from 0 to 1, you can have a sequence of points inside this interval, like xn, which they converge to 1, to x equals to 1. So you can have a sequence of points here which converge to a point which is not inside this interval. Whenever we have that, we say this space is not closed. But for example, we know the closed interval 0 to 1 inside R is closed in the sense that any sequence you take here, if they are convergent, if they converge to something, the limit would be inside this space. So either they would converge in something in the middle between 0 and 1, or they converge to 1, or they converge to 0. So if they're convergent, the limit can't be outside of this set. So in that sense, C0 inside CB is closed. Why? Because if you have a sequence of continuous functions, their limit is also continuous. So what are the functions here outside of C0 inside CB? They are bounded functions. They're bounded, but because they are not inside C0, they are not continuous. But the points inside C0, they do not converge to those functions. Okay? Great. Now, there's one more interesting thing to know. If we have some space which is complete, like CB, which is complete, and we have a subspace which is closed, that would imply this subspace, this closed subspace of this complete space, is also complete. In other words, if you have a sequence of functions Fn, which they are continuous and Cauchy, they are convergent, there's a limit for them, and their limit is also continuous. So if we have a Cauchy sequence here in X0, which means they're also continuous, they converge uniformly to another function f, which that function is also continuous. Okay, any question here? Okay. Now, let's think about, well, we thought about the sequences of functions. Now let's think about series, the sum of some functions. So sometimes we have a sequence of functions like Fn, where n goes from 1 to infinity. Now we can look at their sum. So define F1 to be equal to F1, define F2 to be F1 plus F2, F3 to be F1 plus F2 plus F3, etc., up to Fn to be F1 plus up to Fn. And then we would have say F infinity, which is F1 plus F2 plus F3 up to infinity. Right? So in other words, Fn is the sum of these functions Fi. I goes from 1 to n. Then F infinity is this sum Fi. I goes from 1 to infinity. We just define that. And we want to see when these sums, they really make sense. Okay, so suppose for every x, f of x, f infinite of x would be fn of x, their sum, which n goes from 1 to infinity. The point here is that if we fix one x in the domain, the sum on the right-hand side is not sum of functions anymore. It's the sum of real numbers, because these things here are now real numbers, and we are adding real numbers to each other. Okay. Now, sometimes it might converge for some value of x, this sum. For some values of x, it might not converge. For example, if we think about fn of x equals x to the n, and if I define f infinite to be the sum of these functions, fn of fn, and goes from 1 to infinite. So if x is, for example, 1 over 2, this sum is convergent. F infinite of 1 over 2 would be sigma 1 over 2 to the n, when n goes from 1 to infinite. And the sum is equal to 1. But if x, for example, is equal to 2, of course this thing is not convergent. F infinite of 2 would be sigma 2 to the n, and goes from 1 to infinite. Of course, this sum would be infinite. So sometimes it's convergent, sometimes it's not convergent. Now we would say a series like this, f infinite, which is defined sigma fn, and goes from 1 to infinity, I would say this thing is uniformly convergent, or converges uniformly, if for every x in the domain, whatever our domain is, not only this sequence converges, but also the absolute value of these things also converges. That's the definition. Okay. So a sum might be convergent, but might not have this uniform convergence property. So for example, if fn is -1 to the n over n, this sum would be -1 plus 1 over 2, -1 over 3 plus 1 over 4, -1 over 5, plus etc. Just for one specific, this is suppose this is a constant function. This is suppose it's equal to that for every x. This thing is convergent. But if I look at the absolute value of these things, it would be equal to 1 over n. So it would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus etc. It would actually go to infinite. So the first case, they kind of cancel each other. This plus minus thing, they kind of cancel each other. In the second case, they don't. They add up and they go to infinite. So if something, so sometimes some functions are convergent, like this thing, but they are not convergent uniformly. It means the absolute value is not convergent. Now, about this convergence, there is something, a test called Weistross M Test. Hopefully I'm writing it correctly. Which says, suppose you have a sequence of bounded functions. So suppose each fk is in CB, which is mean bounded, defined on some interval, a to b to r. All of them are bounded. And we want to study this sum of k goes from 1 to infinity. Now, the point is that this thing would be, it would converge. Okay, I think, sorry, I think I chose the wrong name. We were using convergence uniformly for something else. Let's use, I'm sorry, it seems I'm a little tired. It would, I would say it would converge absolutely. Am I right? Yeah. I would say it converges absolutely if the absolute, well, it's about absolute value, so it converges absolutely if the sum of the absolute values is also convergent. Sorry. I would say it converges uniformly if it's really converges uniformly in the sense we just talked about. Converging absolutely means also the absolute value, the sum of these absolute values would also converge. That was my mistake. So we have this sum. Suppose there are numbers, also suppose there are numbers, real numbers mk for every k, such that the supremum norm, which we just defined, the supremum of f of x for all x, the supremum of fk for every k is less or equal than mk. Okay, and the sum of these numbers mk, k goes from 1 to infinity, this sum, suppose this is the sum of real numbers, these are not functions. Suppose this sum is convergence. Now, this sum, sigma fk, this series, this infinite series, this, then the theorem says this sum is convergent both in the uniform way and in the absolute way. I would not prove this theorem. It's not actually hard, but let me see. Yeah, let's prove that. It's a good practice. Let's see why this is correct. So we have a sequence of functions. Each of them is bounded. They are defined on finite closed intervals. Now I'm assuming each function, if I look at its sup norm, is the sup norm is less or equal than some real number mk. Also, I'm assuming the sum of these real numbers is a convergent series. Now I'm telling you that implies this sequence of functions, sigma fk, is convergent both uniformly and absolutely. That's the theorem. Is the theorem clear? Is the statement clear to everyone? That's called the Weistross M test. Is there any question about the statement? Okay. So let's look at the proof of this theorem. So what does it mean for this series to be convergent? Well, it means if you look at the sum from k equals to 1 up to some n, okay, not to infinity, but to some n, that partial sum gives you a function. Call that fn. Okay. We say this sequence is convergent if this sequence fn is convergent, right? As n goes to infinity, as this n is going to infinity, this n is going to infinity. So I want to say, if you look at the partial sums, and at each step, if you add one more function, this sum is convergent. But now we know something. We know that the set of bounded functions is a complete set. So because we know CB is complete, we just proved, it means if I prove this sequence, if I prove it is Cauchy, it would imply it is convergent, right? CB is complete, which means if a sequence is Cauchy, it would be also convergent, right? So I would try to show this sequence is Cauchy rather than showing it's convergent. What does it mean to be Cauchy? Being Cauchy means the elements of this sequence themselves are getting closer and closer to each other. So being Cauchy means if you look at some fn and some fm, their distance is becoming, this distance can be very small. If n and m are large, this distance is very small. But what is this distance? This distance is sup of fn minus fm. Without loss of generality, let's assume n is greater than m. Doesn't really matter. What is fn? Fn is sum of the functions sigma f, say I or fk. K goes from 1 to n. What is fm? Well, fm is also sum of fk, but here k goes from 1 to m. So a lot of k's here, they cancel each other, right? Because this thing is, say, f1 plus f2 plus up to fn, and then we are subtracting the second sum, which is minus f1 minus f2 minus fn. So these things would cancel each other. So the result would be fm plus 1 up to fn. The other terms, they would cancel each other up to m. So we would have m plus 1, m plus 2, etc. Now we can use the triangle inequality. Yeah, that is correct. Exactly. So by triangle inequality would be less than fm plus 1 plus up to fn. But now we know each one of these things is less than mk, mm plus 1, m plus 2, etc. So this is less than m plus 1 up to mn. Right? Now let's go back for a second. We are assuming this thing is convergent. Any convergent sequence is also Cauchy. So if this is convergent, this is also Cauchy. So if I call this thing, if I call this thing, say, I don't know, n, if I call this to be the sum mk, k goes from 1 to n, this sequence, as n goes to infinity, we said this is convergent. If it's convergent, it is Cauchy. So nn minus nm, this thing can be made very small if n and m are large. What is this difference? This difference is m plus 1 plus mn. But these are just real numbers. Actually, I don't need to use norm. They are just real numbers. Furthermore, they are positive. They are non-negative real numbers, right? Why they are non-negative? Well, they are greater or equal than this norm. This norm is 0 or positive, right? It's a norm. It's 0 or positive. So this one is also 0 or positive, can't be negative. So this absolute value is just equal to mm plus 1. They're all non-negative. They're positive or 0. Because this is Cauchy, this thing should go to 0. So this also goes to 0 if n and m are large. Going back to our proof, it means this thing is going to 0. If this thing is going to 0, this thing is going to 0. If this thing is going 0, this sequence is Cauchy. Because this space is complete, any Cauchy sequence is also convergent. So this sum would be convergent. Is there any question here? So it was a nice result, a nice corollary of the theorem we saw earlier, that CBE is complete. Now, finally, we get to the question we are very close to the question we started with. So we are getting close to our main motivation for these things. I try to not go much into the proofs, but it's also very important practice because it's an analysis course. Suppose we have a sequence of functions fn, okay? Suppose they're bounded and integrable from an interval a to b to r. First of all, is it, I think we talked about this, let me raise this question again. Is it correct that if I take integrals of these functions from a to b, and then take limits as n goes to infinity. Is it correct that it's equal to the integral of the limit of fn of x dx from a to b as n goes to infinity? This is not correct. I asked a very similar question. It's a slightly different, but they're similar. So in general, this is not correct. Not correct in general. In general, we cannot change the place of integral and limits. Why is that? Let me give you an example. Suppose fn is this function. Suppose it's defined from 0 to 1. Okay. Suppose from 0 to 1 over n, the value of fn is equal to n. And after that, it's equal to 0. Okay, so for example, f1 would be equal to 1 on the whole interval. f2 would be equal to 2, and then it would be 0, right? Etc. So let's compute these things. What is the left-hand side? The integral of fn from a to b, which here is from 0 to 1, it's the area of the function under its graph, which is n times 1 over n, which is equal to 1. So on the left-hand side, all these integrals are equal to 1. Therefore, the limit is equal to 1. So the left-hand side is equal to 1. What is the limit of these functions? Now let's look at the right-hand side. Let's see what is right-hand side. What is the limit of fn of x for any x as n goes to infinity? Suppose we can just ignore 0, right? Because when we're taking integral, 1 point does not matter. 1 point does not change integral. So what is the limit of fn of x if x is not equal to 0? What is the limit? Well, I guess it's quite easy to guess, right? Let's see how many people know the answer. What is the limit of fn of x as n goes to infinity? Well, this is 0, right? Is there anyone who is not sure why this thing is 0? It is 0 because as we are increasing n, you see, for any point x, if n is very large, at some point 1 over n would be less than x. So x would be the part which f is 0. So this limit on the right-hand side would be 0, and we would have integral of 0 almost everywhere. So the right-hand side would be equal to 0. And as you can see, the left-hand side is not equal to the right-hand side. Okay, so this is not correct in general. But now, what is our theorem? This is the important theorem. If we have sequence of these functions, fn, where they are converging to some other f, but uniformly, not pointwise, then the integral of fn of x dx from a to b, its limit as n goes to infinity is equal to integral from a to b of limit of fn of x as n goes to infinity dx. So the difference here is that we are replacing the pointwise limit with uniform limit, and then this theorem would be correct. So it's a theorem. Okay, let me not go into the proof. Let's just accept this one without proof. this would be a good exercise to think about, to see why this thing holds. It uses a little bit of concepts which we might not be completely familiar with, including measure zero sets. But let's accept that now. But going back to the reason we are studying all these problems, it started by studying Fourier series. In Fourier series, we changed the place of sigma and integral. And the question was, is this correct in general? And we notice it's not correct. However, just like this theorem, there is a theorem which also holds for, is there any question? Also holds for this case. So what is the important theorem here? So again, suppose we have sequence of functions fk. We can add them from 1 to n, call that fn. Suppose as k goes to infinity, as we look at this infinite sum, they are not just converging. This is just the simple result of the previous statement. They converge to some f, which is their infinite sum. But not just pointwise convergence. Suppose this is uniform convergence. In that case, we can interchange the place of sum and integral. So in that case, this is correct. Now let's go back to Fourier series with this. Now we have a lot more information to think about them. Let's go back and see what we can say about them. Let me ask you a couple of questions. Okay, so let's state a few questions. Suppose we have a function f, which is periodic, and suppose we are defined on some interval, maybe from -pi to pi, and suppose we are looking at its Fourier series. And suppose all the coefficients in the Fourier series are equal to 0. So a0, all an's and all bn's suppose are equal to 0. So the Fourier series is equal to 0. Does that imply f is equal to 0? Is that correct or not? That's the first question. Okay, wasn't there a +1 factor involved? If yes, then no. What do you mean by a +1 factor? Well, let's write. So a0 was equal to 1 over 2 pi integral of fx dx from -pi to pi, and an and bn, they're kind of similar. They're integral from -pi to pi, fx cosine nx dx and fx sine dx. So the answer is no, it doesn't. At least if there is no assumption on f. Suppose the function f defined from -pi to pi is everywhere 0, but at just one point. At one point it's equal to 1, but everywhere else is equal to 0. So the function f is not equal to 0, right? It's almost everywhere 0, but just one point. But the point is that its integral would be 0. The integral does not care about just 1 point, right? The integral doesn't care about a few points. The integral would be 0. Also in this integral for Bn, this thing would be 0 almost everywhere. Well, actually, this one would be 0 exactly everywhere. The other integral, fx sine nx, that would be also 0 almost everywhere because f is 0 almost everywhere. So these integrals are equal to 0. But the function f itself is not equal to 0. So we need some extra assumption. So the second question would be, can you guess what is the extra assumption we need to rule out these examples? What is that assumption we should have? That if we have that, if the Fourier series is equal to 0, that would imply the function itself is also equal to 0. What is that assumption?
Continuity, but that might be too strong.
That's a good one, actually. Yeah, that's what I was looking for. That's great. So that is slightly strong. You're right.
Or at
There are
least
weaker conditions.
we could go to continuous on a everywhere but measure 0.
Yeah, that's great. Symmetric around the origin. Well, I mean, we could have this difficulty. Well, this function was symmetric, I guess, right? It was 0 everywhere. It was non-zero at 0, and again 0. So it was symmetric. So the one interesting thing is, for example, if we assume f is continuous, and if the Fourier series is equal to 0, that would imply f is equal to 0 itself too. That is correct. I would just state that without proof. The other day I introduced you the books by Stein. There's one book on Fourier analysis. That's a good place to look at the proof. I don't expect you to know the proof, but if you're interested, that's the place to look. Now, we just talked about when we have this thing that the integral and the sum, they would commute. We can interchange them. And the property we needed was, we want this sum to converge uniformly or absolutely. You say uniformly. Then we would have that. Now the question is that, do we have this in the case of Fourier series? So in the case of Fourier series, we have an, for example, cosine of nx or sine of nx dx. When n goes from 1 to infinity and integral is minus pi to pi. Is it integral to sigma integral of that thing? So we would have this with just the theorem we had earlier. If this would be correct, if this sum converges uniformly. Is that correct? When do we have that? When do we have this thing that this sum converges uniformly? So the theorem we have here is that, suppose we have some function f, right, defined on some interval, say minus pi to r, okay? And suppose we know this extra thing that, okay, I wouldn't state the strongest version. Let me just translate and say something which is useful for us. So in order to have what we want, so we, for example, the one theorem we proved tells us if this sum, say an cosine of nx and bn sine of nx, if these two series are converging uniformly, then we can interchange, then we can interchange the integral of an cosine of nx. Same thing for bn sine of nx and the integral. So this is what we are looking for. So we want these two to converge uniformly. And in many cases, that's correct. A very simple, useful example is if the function f is not only continuous, but it's also differentiable. So we can take derivative of f, and we can take a second derivative of f. And this second derivative is also continuous. In that case, these sums are converging uniformly. So we would say if f is, what is the correct word? You might not be familiar with this word, so let me use something else. Is twice continuously differentiable. By that, I mean we can take its derivative, its second derivative, and the second derivative is continuous. Then these two series are converging both uniformly and absolutely. Also, they converge absolutely. And then, therefore, by the previous theorem we had, these two things are equal. And if you remember, after knowing these two things are equal, after interchanging the integral and the sum, we could compute an, bn, and a naught. So then the rest of what we did is correct. We found like expressions for an, bn, and a naught. So one good assumption is thinking that f is twice continuously differentiable. There is a notation for that. We say f is C2. It means it has two derivatives and the second derivative is also continuous. Okay.
Sorry, I have a question.
Yeah.
You're saying that if f is twice continuously differentiable, then these series converge, but I'm confused though, because isn't an and bn, aren't they defined? Like they're not defined yet.
Yeah, but well, they are defined, but the point is that they are not defined the way we defined them. So you are thinking about them the way I computed them, right? And then you're thinking I defined them by some technique, interchanging them. But the way to think about them is that if the function is twice differentiable, continuously differentiable, it is equal to this sum for some suitable values of an and bn, which we still don't know how to compute, but it is equal to that. And also, there is this property that these sums are converging uniformly. And now I want to compute them. Now the technique I applied is a valid technique.
I see. So you're positing the existence of these an before.
Yeah. So
Okay.
you shouldn't confuse their existence and the specific way I tried to compute them, and I took integral and changed the sum and integral and things like that. The statement here is about their existence, and so it says an and b. So the better way to say it is that if f is twice continuously differentiable, an and bn are finite real numbers. They exist. These sums converging to something uniformly and absolutely. And then also you can interchange sum and integral, and therefore that specific technique for computing them is a valid technique. And therefore they are given by those formulae we found.
Okay, gotcha.
Is it clear enough? Yeah, great. Okay, so it's a good place to stop. I think tomorrow I would kind of review what we did today without going into any proof. And then I think in the first class tomorrow, we would finish this Fourier series, and then we would start with the heat equation. So is there any question? If not, we can stop here. You can ask me any question.